Hello, students. We are into the math connections for 3.4. Math connection 3.4. I've got 1, 4, 6, 8. So a lot of evens. 1, 4, 6, 8, 12 to 14, 16 to 17. So let's take a look at a few of those. Question number one. Why is an odd number times an odd number always an odd number? Okay. My suggestion for this is to think about what makes an odd number an odd number. Okay. How do we define odd numbers? How do we find an even number, right? Maybe that's even easier. So if you had an even number we've already talked about, at least in my other videos, is 2 times a number. 2 times a whole number is an even number. Well, that would be like a what? 0, 2, 4, 6, 8, dot, 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 dot. Okay. So odd numbers would be 1, 3, 5, 7, 9. And if you take a look, you could say, oh, wait. So basically, it just have to be one more than an even number. So an odd number would look like a 3a plus 1. Okay. Multiply that by another odd number. So again, maybe 3b plus 1. And the question, why did I write 3 down? Odd number would be 2a plus 1. I told you it's an even number plus 1. We're going to multiply that by another odd number, 2b plus 1. All right, there we go. So when you multiply these out at the end, if you want it to always be odd, that means it needs to look like 2 times something plus 1. Okay, so if you multiply this out, can you rewrite this to find 2 times something plus 1? If you can, then the result of an odd number times an odd number will always be odd. You can demonstrate why it has to be true. We don't want to verify this by using guessing and checking, and we don't want to verify this by demonstrating with a bunch of cases. Cases are not enough. You could show 10 times it works. It only takes one time for it to fail. Okay, question one. Question four, let's hear, is x times x ever equal to x? That's one I'm going to leave for you. Now, remember, we are dealing with whole numbers here. So think about all the whole numbers you could possibly have, right? Clearly, 3 times 3, 9, is never equal to 3. Okay, that's great, but that's just one example. Okay, so it says, is it ever? So this would be like one of those test questions that some of you like, some of you didn't. I would say x times x equals x. And I would ask you to say, is this always true, sometimes true, or never true? Okay. Even some of the ones that were in the exam, those ones were taken from homework problems just like this. So keep that in mind. That's where I get those problems from. Let's see here. Explain how the distributive property would be helpful to mentally perform this computation. Oh, yes. Look for compatible numbers. Okay. Notice how there's a 37 in each one of these. Let me highlight that real quick. So I see there's a 37 in each one. So that means if I use the distributive property, I could rewrite this as 37 times something. And maybe the distributive property would help me make this multiplication and then addition easier. Okay, let's try that. Let's see here. How would you explain to students how to multiply this, assuming they know and understand multiplication by a single digit and multiplication by a power of 10? So how do you multiply two 3-digit numbers? Again, as you're going through this process, think about those place values. Like you could use a traditional algorithm. You could use the partial products algorithm, whatever you think would be best for this type of problem. I would recommend. And again, it's your chance, right? How would you do it? It's not about what Scott would do. It's about what you would do. Okay, so let's see here, 1, 4, 6, 8, then 12 through 14. So let's see here, there's 10. Oh, we're up over here. Now connecting to the classroom. Here come the students. Sienna claims the following is true by the distributive law. Oh, so if you multiply 3 times AB, then you get 3A times 3B. Okay, how might you help her? Right? What are you trying to do? Hey, is the student correct? They've come up with something, so I want to reward that. I want to be congratulatory of that. At the same time, I want them to see, hey, how'd you come up with this? Maybe did you try some examples? Did you test this? Plug in some values and see if it works, right? Try that. And then if she's correct, make sure you understand why she's correct. If she's incorrect, make sure you tell Sienna why This is not correct, but I can see where you got this idea from. Okay, clearly this comes from the distributive law over addition, multiplication over addition. We would have 3 times a plus b is 3a plus 3b. So she's like, aha, I got it then. It works for multiplication too, and maybe it does. 12, 13, Amy claims no finite set of whole numbers is closed under multiplication. Ooh, no finite set of whole numbers is closed under multiplication. Finite set. If only there was a homework problem. Very, 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 very similar to this. Finite set. No dot, dot, dot out to infinity. Okay. Take the whole numbers. Take out, instead of doing all the whole numbers, start at the number 5 and go 5 and beyond. That set is an infinite set of whole numbers, and it is closed under multiplication. So remember, closure under multiplication does not mean you have to have a way to get each item through multiplication. It's that if I use each item to multiply, that the result will be in the set. Okay. Let's see here. We've got Leia. Ah, yes. Star Wars. Leia performed the following calculations. Use the force, Leia. She said 2 plus 3 times 4, 2 plus 12 equals 14. 2 times 3 plus 4 equals 2 times 7 equals 14. From this, okay, so she used an example, right? Came up with a conclusion. She said, so if I take any whole numbers, then this should work. And you can take a look at her work. Okay, all right, interesting. How would you respond? Right? How would you respond? So I'm going to leave that to you to figure out how you would respond to this student. Again, same type of thing as Sienna. Are they on the right track? Is the work they did to this point correct? Can we try some other examples? Is it always true? If not, if so, give some feedback to the student. What did I say? Through 14, 16, and 17. Okay, so student performance following computation. Explain the meaning of the 4 above the 6. Yeah, you need to know what that 4 means. Explain the meaning of the 3 in the hundreds place. Okay, the 3 in the hundreds place. Okay, I think they mean this 3. Don't think they mean that 3 because that 3 is kind of floating above the hundreds place. Okay. All right, so anyway, that's what the student performed in their computations. Let's see here. I would probably give, if I was doing a test, I would give you something like this with the work already done, but I would probably give you a 2-digit number instead of a single digit. I'm not going to lie. This single digit, I don't think that demonstrates the issues that students are going to have. So we'll keep that going. And here's 17. Now we're doing computation in base 5. Explain the meaning of the 3 above the 3. And I believe they're referring to this piece right here. I would have said the 3 above the 3 in the factor. Remember, the word factor means the things you're multiplying. So I would have said the 3 above the 3 in the factor. But what does that 3 represent? Okay, we got to know when we're writing a number down, we should know what it means. If you're really interested in some other cool stuff, there are some other cool pieces here. This has made the rounds on TikTok, on Facebook, on Instagram, people saying, hey, look at this cool way of doing it. It's a multiplication, and sometimes they'll say it's the Japanese line method, occasionally, or the stick method. What do they call it? The multiplication, stick multiplication. Okay. I don't know. Everybody always draws it. They never lay 6 down typically. But what you're looking for is these kind of intersections, and then you would add them. So you kind of would take the digits on the right-hand side, which would be like 6 pieces here, and you'd put those in your ones place. Then you add all of the little intersections in the middle, and that becomes your tens place, and then things on the left-hand side become your hundreds place. And hopefully you can see a nice little connection between this and lattice multiplication, or this and the traditional algorithm. And we'll see if you can make that connection, because I think it is a pretty good one. Let's see. I think I said group work 2. Did I say group work 2 for this one? I did. So group work number 2, messages can be coded on tape in base 2. A hole in the tape represents 1, and absence of a hole represents 0. Okay. Decode the message below. There we go. Letters of the alphabet may be coded in base 2 according to the position in the alphabet. So that is 100% true. This is a fantastic code. And to be honest, I really think elementary students would love this. I have done it with slightly older students when we do this STEM. This used to be the STEM Festival. Now it's the Stream Festival. And kids love making codes. And so anyway, if you have kids that love making codes, there you go. So as an example, you can see if you put little holes kind of in these place values, and if you need to draw the lines in for place values, that might be helpful to you. I know when I was doing this, I was like, I kind of need those lines in here. So I would recommend putting the lines in. These are your place values. So you have 1s, 2s, 4s, 8s, and 16s. We don't need to go any higher because the next place value would be 32, but our alphabet doesn't have 32 letters in it. So we just need symbols to represent each of the letters. And we actually have a little bit too many. We would have enough to do 31 letters, but we only have 26 in our alphabet. So this might also work well with some alphabets around the world that might have a few more characters than ours. Okay, so again, if I wanted to represent, let's see here, the letter M, it says write your name on tape using base 2. So if I'm going to give a hint, right? I'm going to give a hint. Okay, so my name, if I was doing my name, I need to find the letter of the alphabet. Okay, well, there's 26, right? 26 would be, the 26th would be Z. So Z, Y, X, W, V, U, T, S. Okay, so 26, 25, 24, 23, 22, 20. So there's 20, 19, 18. Okay, so S is 18, T is 19. Okay, so if I was doing this and I wanted to represent the letter S in this system, I would need, and I'm going to put a little bit of white out over this just temporarily so you can kind of see just the piece that I'm doing. If I was doing this and I want to think to myself, how many 16s are in my number? And there would be one group of 16. So I'd put a little dot, a little hole there. That takes out 16 and leaves me with 2. And then that would mean don't put anything for 8. So kind of like no 8s, no 4s. Yes, there's a 2 and there's no 1s. And I think that's the piece where, as you're doing this, if you were doing this yourself, you just need to remind yourself, don't put anything where those X's are. This would be the letter S. The letter C, what is it? A, B, C. So it's the third letter. So if I was doing the letter C, then I would ask myself the same question. Are there any 16s? No, there's no 16s. There's no 8s. There's no 4s. In order to form the number 3, it would just be a group of 2 and a group of 1. And so when I come back and redo this, I'd say, okay, just the 2 and the 1. So the letter C for my name would be, would look like this. 2 little holes. Okay. All right. Anyway, I think that's kind of a fun one. I hope you enjoy it as much as I did. And that'll wrap it up for now. All right. Off you go.